Our first speaker, as you can see from the slide here, is going to talk about a natural interface for multifocal plane head-mounted displays using 3D gaze. And we have researchers from two different organizations, Takumi Toyama and Daniel Sontag from the German Research Center for Artificial Intelligence, and Jason Orlowski, who will be giving the talk, and Kiyoshi Kiyokawa, from Osaka University. Thank you.
Great, thank you for the introduction. So again, my name is Jason. I'm a second-year PhD student at Osaka University, and here we go. Okay, so first of all, to introduce the problem, we have lots of nice displays coming out these days, like Google Glass, Epson's Moverio, Brothers Air Scouter, and lots more to come, I think. But there are still a lot of problems with these displays. In particular, when we overlay content onto the real world, we can occlude things that we want to be looking at. For example, if there's an oncoming car, oncoming pedestrians or bicycles, we want to be looking at those and not have distracting text in the way. So that's the problem we're trying to solve here. And you can see to the right is a view taken through a head-mounted display of text overlaid onto a few bicyclists in the environment. So how are we going to solve this problem? In a nutshell, we want to quickly close or dim distracting text via an eye-tracking interface. So there's some eye-tracking interfaces available, but none that take advantage of multiple focal planes, which we also prototyped a multifocal plane head-mounted display. And using the knowledge of the depth of the focal plane, or the distance at which something is displayed, we can very quickly know where a user is looking at an environment and dim that text. So up to now, so I'll give you a little history of the multifocal plane displays and sort of their progression towards head-mounted displays. About 10 years ago, there was something that was called the depth cube, which is a multifocal plane. Actually, looks like a TV, like a monitor. So, multifocal plane monitor, which allows you to project the correct distances of certain objects. So, if you're looking at just your LCD monitor, you only see a single focal plane. You can only display things at one depth. But these devices allow you to display them correctly, or more correctly, so to speak, at different distances in the environment. So these basically, prototypes have become better and better, and a second one by Ackley in 2004 was more designed towards testing perception. So how do people perceive things at different depths? So in the real world, we have sort of an infinite number of depths that people can be looking at. So how do we sort of replicate that in a display? More recently, the development of liquid lenses, or lenses that have a varifocal, meaning you can change the distance of the focal distance in real time, by Liu in 2010, and then most recently at ISMOR last year, computational AR glasses, which basically allow you, it's a light field display, I believe, and it allows you to computationally determine the depth, or project the correct depth at which someone is looking at something in the real world. So these are nice, and you can see that they're sort of getting lighter and better. Unfortunately, the computational AR glasses are still very computationally intensive. I think it's a minute per frame to display correctly, so not quite there. So the second half of prior work is basically studies on depth perception. So how do people perceive things? So for example, textured objects, or for example, blur. People perceive those as being at different depths, even though they may be projected at the same depth. So we draw a little bit from that field during our experiments, which I'll talk about later. And there have also been some studies about perception in 3D displays, as well as for interaction. So one study by Kwan in 2006, people were actually able to use an eye tracking, actually started as a camera that tracked their head and eyes, and they could select objects in one of those static 3D displays. So even though we have different planes and different locations in the planes, it is possible to track stereoscopic vision in that case. And then we have a few other methods that use line of sight for interaction and augmented reality. So for example, how do we select objects in the real world, or the virtual world for that matter? How do we know when someone is looking at a virtual object versus a real object, for example? And how do we manipulate those? So we basically draw from all these fields in our method. So a lot of these 3D displays are very static, so they look like a monitor. It's something you place in front of you. It's not something that's wearable. So we need a mobile solution, something you can walk around with and still display different focal depths. Secondly, we don't know if stereoscopic depth tracking works in a monoscopic display. So if only one eye is looking at something, can we still track the depth, because we need two eyes to calculate depth? Can we do that? If so, how accurately? And lastly, most gaze methods are line of sight. In other words, they're a single line towards something, so you don't know if you're looking at something mid-distance or behind that. So we sought to solve that problem as well. Okay, so first of all, we set out to construct a multifocal plane head-mounted display. And to do that, we used a series of 3 air scouters, and I'll describe why we chose 3 and why we chose these particular distances. So they're aligned right in front of each other at 30 centimeters, approximately 1 meter, and anything beyond 2 meters, right in front of the eye. And those distances and the number of planes were selected based on a pilot experiment, which I'll talk about later as well. The second part is the eye tracker itself, and we chose a commercial product, which is the SMI eye tracking goggles, which is a pretty standard device. The difference is that we have a 3D printed connector that attaches the display to the eye tracking device. So this does a couple things. One, it fixes the distance between the display and the eye tracker, and it also fixes the angle at which people are looking at content, which helps with accuracy in the end. So for those of you that don't know the eye tracking interface, there's an environmental camera, so we know what people are looking at in the environment, and 2 inward-facing cameras to do the eye tracking. So this is what the prototype looks like. It's a little bit bulky, but you can see on the left we have 3 different focal planes. They're attached to the 3D printed tracker to the SMI goggles, and this is how people took the experiment. So, as far as software is concerned, we have 2 primary goals. One, and the most important, is to remove distracting text. So, if you're walking around the environment and a car is oncoming and you want to judge how fast that car is coming or from where a bicycle is coming at you, you don't want to see anything on the screen. You want to have a clear view of the environment. So, removing that text, doing it quickly, doing it accurately, and also, so the eye tracker has a tendency to move on people's faces. Despite bad gaze data, we still need to be able to remove text robustly. And lastly, we don't want something that people are going to have to reach up and tap something or press a button to distract text. We want them to be able, just as they look at a different object, we want the text to disappear almost as magically, or automated, basically. And then as a secondary goal, once people have moved their gaze off of the display, we want them to be able to re-engage text once they look back into the display. So, first of all, eliminating distracting text. So, this is basically based on plane changes, and you can see here that these are the 3 planes basically a 2D model of the 3 planes within the display. And sort of the most simple case is when someone is looking at text and there's a car that's off the display. And so, very simply, if someone moves from the plane to the environment, we basically close text. And I'll describe the eye tracking process in a little bit as well. The second and slightly more complex case is when someone is they gaze from one plane to an object in an environment that's occluded by another plane. So it's the same line of sight, but at a different depth. So, if it's at a different depth, we calculate the depth, and if there's no content on the screen, so you can see the car in the upper right here, if there's no content on the screen, but they are, because we know where content is on the screen, but they are looking at the environment, then we also did the first plane. So whenever there's a plane change, not to new content, that's when we close. And I'll have a demo video later to show you how it works. So the second goal was reselecting text. So how do people reselect text once it's back on? This is a little bit closer to typical methods that are line of sight, but we also gain some advantages by calculating depth, not just line of sight. So it basically requires a dwell time. Someone looks at a virtual icon, which is left on the screen. So for example, we have the text here, which might be dimmed. And then secondly, an icon is left in its place. So something that's not distracting, that's not going to occlude cars or other distractions in the environment, and that's not going to interfere with them making depth judgments or occlude dangerous items. So once they look back into this onto this icon, the text will be redisplayed, and they can continue their walking tasks or whatever it is they're doing. But this still does need usability testing. So, how do we find the gaze plane? So typically, we found in the experiments that it's actually not very easy to track a depth accurately in a monocular display using stereoscopy. So what we do to get an approximation of depth is we use what's called support